thermodynamics. Okay. So thermodynamics is all about energy. So today we're going to talk about how energy plays a role in chemistry. And to start, let's look at some of the different kinds of energy. So here I have a picture of a nuclear power plant. Okay. So you have a nuclear power plant. So this turns like uranium fuel into energy, which electricity, which we can use in our homes. Okay. So first of all, so we have some different kinds of energy. We have kinetic energy. So this is energy that comes from movement. So an example of kinetic energy might be we have a stream next to our nuclear power plant. So this stream is moving at some velocity. So kinetic energy can be approximated as like 1/2 mv squared. So the water in the stream has some energy associated with it. Okay. So inside this nuclear power plant, we have a steam turbine, which is rotating at like maybe 1,000 RPM. So rotating very, very fast. So that's, it has some rotational kinetic energy. So this rotation has energy. So you can think of it, this would be called like mechanical energy. So we have rotational and mechanical energy. So we also have heat energy. So the radioactive decay of the uranium inside this reactor generates a huge amount of heat. So it generates a huge amount of energy as heat. And this heat goes into boiling the steam. So, and then the steam drives the generator, which turns drives the turbine, which turns the generator, which generates the electricity. So we have heat energy. And also, we have nuclear binding energy. So so uranium is decaying into smaller atoms, and these smaller atoms, there's a certain amount of energy that holds the protons and the neutrons in the nucleus together. And you know Einstein's famous equation E = mc squared, right? Well, it turns out when you combine a bunch of protons and neutrons to form a nucleus, the mass of that nucleus will be less than the sum of its parts. So there will be a very slight mass difference between the mass of the nucleus and its constituent particles. And this mass gets turned into energy. So in order to break apart a nucleus, we have to input a large amount of energy. So yeah, when we turn uranium into lighter elements with smaller nuclei, those smaller nuclei actually, the sum of the masses of all of the particles that a uranium nucleus will turn into is less than the mass of the original uranium nucleus. So we get so that mass difference actually gets converted into energy by E = mc squared. So nuclear binding energy, and obviously electrical energy. So this whole nuclear power station is generating energy in the form of electricity. Okay. So this is all goes to show how different kinds of energy can be converted into each other. So in a nuclear power plant, we have nuclear energy getting turned into heat energy, which boils off steam, which goes into a turbine, which creates rotational or mechanical energy, which then gets converted into electrical energy. And then at the consumer, that electrical energy will get converted into some other form of energy that is useful. Okay? So for example, the light bulb here or the computer here, light energy. So what is so thermodynamics, we have to establish a few definitions. So thermodynamics is about like the universe. So the universe comprises the system and surroundings. So for example, here we have some chemical apparatus. So all of this tubing is to create an air-free environment because the oxygen in the air will often react with some sensitive compounds. So I believe here is a Birch reduction. So they're using lithium in some kind of alcohol with some solvent to reduce aromatic compounds. So it's called the Birch reduction. And because you have sodium, which is very, very reactive. Oh, yeah, it's in liquid ammonia. So we have liquid ammonia with some alcohol and dissolved lithium. So the lithium is very reactive with air. So this apparatus needs to be kept completely air-free. So we use this apparatus called a Schlenk line to, so this is pressurized with nitrogen gas. So inert nitrogen gas. Okay, so you have some system, and then outside of the system is the surroundings. So the surroundings is anything that's not the system, okay? So what if the first law of thermodynamics is that the energy in the universe is going to be a constant. So this is called conservation of energy. So any energy that the system absorbs has to come from the surroundings, or if the system outputs energy, that energy has to go into the surroundings. You can't make or create energy or mass. Mass and energy are really the same thing. So because of E equals mc squared. So for example, if you've ever seen a refrigerator, you probably have a refrigerator in your house. So you might have noticed at the bottom of the refrigerator or the rear of the refrigerator where it faces the wall is actually usually quite warm. So why is the refrigerator, which is supposed to cool stuff down, warm? Well, the stuff inside the refrigerator is being lowered in temperature. So that means it's losing energy, and that energy has to go somewhere. So the job of a refrigerator is to remove energy from your food and expel that energy back into the atmosphere, the surroundings. So energy is conserved, okay? So now we want to talk about changes in energy. So I wanted to find something called internal energy. So internal energy is usually represented with a U, but you might see it represented by a capital E. So either a capital U or a capital E. So U represents the total energy of the system. So you might not be able to see this internal energy, but all of the particles in something are all vibrating, and they're all rotating, and they're all doing transformations in space. So because of this, they have an associated energy with them. So internal energy is really the sum of all the energies contained within that system. So whether it's kinetic energy or potential energy from molecular attraction or nuclear binding energy, et cetera, et cetera. Okay. So it turns out that it is impossible to actually determine the internal energy of a system, right? Because it's impossible to determine the sum of the kinetic energies and the potential energies of all of the particles in the system. But what we can do is we can determine the change in energy. Change in internal energy, represented by delta U. So delta means change. So this delta means change. You might have seen that in your math classes. So we have change in internal energy, and this equals the internal energy of the final state minus the internal energy of the initial state, which I've represented by UF and UI. So change in internal energy. And remember that, this should say surroundings. This should say surroundings. So the change in energy, change in internal energy of the universe must remain a constant. So therefore, if we have the system has some change in internal energy, that will be equal to the negative change in internal energy of the surroundings. So let me fix that. Surroundings. So delta U cis equals negative delta U of the surroundings. Okay? This makes sense because if we sum these together, we get 0, which is, of course, the change in internal energy of the universe, which must be 0 because of the conservation of energy. Okay. So delta U in thermodynamics is, we can often say it has two components. We have heat and work. So heat is like self-explanatory. It's heat. Heat is different from temperature, though. Temperature is kind of a measurement of how much like heat, I guess. You can think of it that way. But it's important to remember that heat and work are different. So, for example, if we boil a small pot of water and a large pot of water, they will be at the same temperature, but the amount of heat energy that we need to put into the larger pot is going to be much larger than the smaller pot, okay? So, and then work, you might remember work equals force times distance. But in chemistry, the most important kind of work, and there's so many different kinds of work, but the most important kind in chemistry is what's called PV work. So this is work done by expansion and contraction. So chemical reactions will produce gases or they consume gases. So this results in some contraction or expansion. So we have W equals negative P times delta V. And don't worry about the negative sign. This is just a sign convention to make stuff work. Often in physics, you'll see work equals positive P times delta V, but in chemistry, it's going to be negative. So this is very important to realize. So if a system does work, then work is negative because when it does work on something else, it's losing energy. So W should be negative. If you do work on the system, so if something does work on the system, then the system will increase in energy, hence work should be positive, which this is a major point of confusion often. So for example, let's imagine some hypothetical engine, like a car engine. So let's say I add 100 joules of energy to this engine, and it does 200 joules of work. So then what should delta U be? So it does 200 joules of work. So W equals negative 200 joules, okay? And then we add 100 joules of heat energy. So it's 100 plus negative 200, which equals negative 100. So delta U equals negative 100 joules. Yeah. And one final thing. When we do this PV calculation, pressure is going to be in pascals. And volume is in meter cubed because we want to have SI units. But often we don't use these in chemistry because they're inconvenient. We use atmospheres and liters. So you might want to write down that 1 liter times atmosphere equals 101.3 joules. So you can just write this conversion down. It might be helpful later. So 1 liter atmosphere equals 101.3 joules. And you can see this from the different values of the ideal gas constant. Okay. Okay. So now I want to talk about a concept called enthalpy. So enthalpy is defined as the internal energy plus the pressure times the volume that system holds, that system has. Okay. So it's internal energy plus the pressure and volume times the volume of the system. Okay. So why is H useful? Well, look at this derivation here. So we have delta H equals delta U plus delta P times V, right? So change in enthalpy. Yeah, so what I did forget to mention is that although we cannot measure enthalpy and we cannot measure internal energy directly, we can easily measure changes in enthalpy and changes in internal energy, which are really what are important in chemistry, okay? So we do this derivation equals delta U plus delta P times V, and then delta U, remember, equals Q plus W, and then W equals negative P times delta V, and then this stuff cancels, so this stuff and this stuff cancels out. So we have delta H equals Q at constant pressure. And most reactions happen at constant pressure. Most reactions happen at 1 atmosphere. So this means that we can very easily measure changes in enthalpy using what's called a coffee cup calorimeter. Okay. So we have a coffee cup calorimeter here. So coffee cup calorimeter. So we have this well-insulated container which limits the transfer of heat. And then we have some chemical reaction. And this chemical reaction will release some heat, which we can measure as a change in temperature. And then we can easily convert this change in temperature back into heat. And then from the heat, we can calculate delta H of the reaction. Okay. So just remember that enthalpy equals U plus PV. Okay. So now we can have delta H of reactions, which is really the crux of the lecture. So change in enthalpy of the reaction. Well, if we have a reaction that goes from reactants to products, the change in enthalpy should be the sum of the enthalpies of the products. Oh, that's a mistake. There should not be a delta symbol. This should not be here. So change in enthalpy should be the sum of the enthalpies of the products minus the sum of the enthalpies of the reactants. So that's what the sigma here stands for sum. So let's say we have A plus B goes to C plus D. Then delta H should equal the enthalpy of D plus the, I guess I can write it as equals enthalpy of D plus the enthalpy of C minus enthalpy of A plus the enthalpy of B. Right? So this is basically what this means when we say, so sum of the enthalpies of the products minus the sum of the enthalpies of the reactants. So if enthalpy is if delta H is positive, then the reaction is endothermic because the enthalpy is increasing, hence it's absorbing heat from the surroundings. Okay? If delta H is negative, the reaction is endothermic. If delta H is negative, the reaction is exothermic because enthalpy is being lowered, so we're releasing energy into the surroundings. So it's exothermic. So exothermic reactions release heat and vice versa. So here I have an interesting photo. So we have what appears to be ice burning. So here's the chemical reaction that's going on. So we have calcium carbide, which is interesting compound, plus some water. You can balance this yourself. Goes to calcium hydroxide plus acetylene. C2H2. And so basically the ice melts and it generates water, which reacts with the calcium carbide to form acetylene. And acetylene is highly flammable, so this acetylene can then be lit on fire, and the fire melts more water, which reacts with more calcium carbide. So you get this very interesting effect of what appears to be ice burning. So for the combustion reaction, the acetylene reacting with oxygen in the air to release heat, do you think delta H is positive or negative? Right. So we're releasing heat. So we're releasing heat, so delta H is negative, right? What about the melting of water? Do you think the melting of water is delta H positive or negative? So when we melt water, we are adding energy to the water because we have to add energy to break the bonds between water molecules to go from this rigid crystal, this ice, into a liquid where the molecules flow freely. So we have to input energy, and because we're inputting energy, is it positive or negative? So since we're inputting heat energy, the enthalpy will increase, so delta H is positive. So here we have two different reactions going on. We have the burning of acetylene, which has a negative delta H, and we have the melting of water, which has a positive delta H. Okay. Oh, by the way, so back in like the early 1900s when they didn't have electricity, they didn't really have electricity. So how did they make car headlamps work without electricity? So basically, you would take a canister of calcium carbide and you would very slowly drip water onto it. And this calcium carbide can be ignited. The acetylene gas, which is produced, is then ignited. So that's how they would use to do really old-fashioned headlamps. Okay. So, does anyone remember what a state function is? So, a state function is something that does not depend on how you get to it. For example, if I wanted to go to London, I could either take a plane to London or I could take an ocean liner to London. I don't think you can ride a bike. I don't think you can drive a car to London. I don't think you can drive cars on water. But regardless of how you get to London, you're going to still be in London. So your location doesn't really depend on how you get there. Likewise, internal energy doesn't depend on how you get there. You can increase your energy by having work, or you can change energy by using heat. It doesn't matter. So internal energy is a state function. And it turns out pressure and volume are also state functions. It doesn't matter how you increase the pressure, you're still going to have some pressure. So some arbitrary amount of pressure. So enthalpy is a state function. So state functions are very important because we can add them together, okay? So for example, let's say we have A goes to B, 2B goes to C, and then D goes to C. Okay, so we want to find the delta H of A goes to D. So then delta H equals A goes to B plus this divided by 2 plus this divided by 2. So I forgot to add the divide by 2 here. So let me, right. So let's imagine it this way. Okay, what do we have? So now we can multiply this one by 1/2. This one stays the same. And then delta H. So we have 1b and we have 2b's here. So we need to divide this by 2. So multiply by 1/2. Okay? And then this is supposed to be d goes to c. Now we want this to be 1/2 c goes to d. So we actually need to multiply this by -1 and then by 1/2. And then when we sum this all together, so a goes to b, b goes to 1/2 c, 1/2 c goes to 1/2 d, and then sum this all together, we have delta H equals delta H1 plus 1/2 delta H2 plus -1/2 delta H3. So what's some justification for this? Let's imagine we have two states, A and B. And on the y-axis, we have enthalpy. So if we go from A to B, we have this change in enthalpy. So we can call this delta H. However, if we go in the other direction, the change will be the negative. So in this way, in that direction, it should be negative delta H. Okay? And so if this is A, then this is going to be 2A. If this is B, this is 2B. And then this difference, the difference between 2B and 2A is going to be 2 times delta H. Okay? So what's the takeaway? If we want to combine two reactions, all we do is add their delta H's. Okay? If we multiply a reaction by some integer n, or it doesn't have to be an integer, just some number n. So NA goes to NB, where n is just any number. Delta H equals n times delta H1. So delta H1, delta H1. If we reverse a reaction, then the delta H becomes negative. Okay? So here's an example. Let's say we have this reaction. This might not be, the numbers might not be exact because I'm just remembering this off the top of my head. So delta H, if I remember correctly, equals negative 50.4 kilojoules per mole. So can someone compute the delta H for this reaction? Can someone do this? Okay, so how do we get from this to this? How do we go from here to here? So how do we go from here to here? Great. So we have to reverse it, and we need to multiply it by 2. Perfect. So when we do that, when we apply your transformations to our value of delta H, what's the new value of delta H? What is our new delta H? So yeah, we need to reverse this and then multiply by 2. So what should be the new delta H? Great. So negative 100.8, right? Okay. Great. So I think we got this. And seeing how to add these reactions together to get the right reaction takes some time. So just practice, I guess. So, okay, great. So now imagine we're a chemist and we want to get some data on reactions. Well, obviously it's impossible to calculate the delta H, to measure the delta H for every reaction. Remember, delta H is going to be, it's an experimental value. So someone actually has to do this reaction. They have to get their calorimeter and they have to measure change in temperature to find these values. And there are maybe 1 billion different chemical reactions out there, so we can't possibly measure the delta H individually for every one of those reactions. What we can do, however, is tabulate values of enthalpies of formation for all the molecules out there. And it's actually not too difficult to do this. We can tabulate these values based on other reactions or direct measurement. And then using that, we can calculate the delta H for any reaction in the world, whether that reaction actually happens or whether it doesn't. So what are these enthalpies of formation? So notice that, so we write this as, so delta H of formation, and then we have this little circle here. So this circle indicates that we are at standard state. What does standard state mean? It means we are at 298 Kelvin. So room temperature is about 298 Kelvin. We are at 1 atmosphere of pressure, and all concentrations are 1 molar. Okay? So those 3 things, we have 298 Kelvin, 1 atmosphere, all concentrations are 1 molar. So 1 mole per liter. Okay? So delta H of formation, delta, and the circle is often called naught. So delta H of formation naught is the, so the delta H for the reaction that makes 1 mole of the substance from its constituent elements at standard state. So 1 mole of the substance, okay? So this means you will often have some weird fractions in your equation, but that doesn't matter. All that matters is that the product is the enthalpy is what you want. The product is what you want, and there's 1 mole of it. So let's say we want to find the enthalpy of formation for sodium chloride. So we have sodium plus chlorine goes to sodium chloride. Notice that sodium chloride is the only product. We're only producing sodium chloride. Furthermore, there's only 1 mole of sodium chloride. So additionally, our sodium is going to be solid, okay? So solid because at 298 Kelvin, sodium is a solid. Chlorine is going to be a gas too. And notice we have this 1/2 coefficient in front of the chlorine, okay? Because we need to produce only 1 mole of sodium chloride, which requires only 1/2 mole of chlorine gas. So let's say we were to write this. This is incorrect because we're producing 2 moles of sodium chloride. We're producing 2 moles of sodium chloride. We want to produce 1 mole. Furthermore, sodium is not a liquid at 298 Kelvin, so this is not at standard state. So you might be wondering, how do we figure out what form it is in standard state? Well, a good rule of thumb is to remember that at standard state, you want to pick the form of the element that's most stable. So for example, if we want to put carbon in this reaction, if we had a reaction that involved carbon, there are many different kinds of carbon. We can have Buckminster fullerenes, we can have diamond, we can have graphite. Well, it turns out that the most stable form of carbon is graphite. So we use graphite. The one exception to this is phosphorus. So the most stable form of phosphorus is black phosphorus, I think, but we don't use black phosphorus, we use white phosphorus, okay? So, and we only start from the constituent elements. On the reactant side, for delta H formation, there should not be any compounds. We only want pure elements, okay? So, why is this useful? Well, delta H of a reaction equals the sum of the enthalpies of formation of the products minus the sum of the enthalpies of formations of the reactants. There should probably be a circle here. I think it would be probably good to put a circle there, but it's not super important, the difference. So see? So write this equation down or memorize it. And why is this? So I guess I can illustrate it with an example. Let's say we have, so let's do a simple one. When we think of a very simple reaction. Okay, how about this? So H2 plus, and then CH4, and then we have to balance this, so that should be a 3. Okay, so let's do this reaction. So this is a very industrially important reaction. Okay. So, okay. Oh, I think this is wrong. It should be, yeah. Well, regardless, this is still fine. I think it should be water. Yeah, it should be, we can look at an easier one actually. So the water gas shift reaction. So this is how we produce hydrogen. Okay. So the water gas shift reaction. So what's the delta H of this reaction? Well, the delta H equals the sum, the delta H of formation for the products minus the sum of delta H formation of the reactants. Okay? So this should be, it should be the delta H formation of H2 plus delta H of formation of CO2 minus delta H formation plus of H2O, right? So, how can we justify this? So let's look at the individual delta H's. So first of all, delta H formation of H2. So this corresponds with the reaction. Oh, sorry, it should be. right? Because hydrogen itself is an element. Hence, delta H equals 0. Delta H of formation, H2 equals 0. So the enthalpy of formation for all of the elements at their standard states is 0. Okay. What about CO2? So this corresponds to carbon plus oxygen goes to CO2. And then we can repeat the rest. And then water. Notice we have 1 mole here, 1 mole here, 1 mole here, always 1 mole in the products. So if we take this, we need to take this one. If we take that reaction, and then we subtract these, so we subtract these, we get this reaction, right? So it's kind of hard to see this, but I guess you can think of it as like subtracting these would be the same as adding the reverse. So you can reverse these two reactions and then add them all together, and then we get this original reaction. And that corresponds to taking this one and subtracting these two, which is of course the expression we have here. And you might, and of course I'm ignoring this one because this is just 0. So it's convenient to ignore it. Okay. So, okay. So just to illustrate how this whole thing works, and we can of course tabulate values of these enthalpies of formations for all of the chemicals we want, and then just calculate delta H for any reaction we want. So imaginary or real. So let's see if I can find some problems related to this. Okay. Let's see. Let's look at problem 8. So it's multiple choice. All of these are going to be multiple choice. How come I can't open up the chat? Okay. So we're given this data. We have a bunch of data here. So can someone calculate this? Can someone do problem 8? And I'll do it too. Because of some, yeah. B, C, D, or E. So can we do 8? So notice all of the data is here. So here are our standard delta H of formations. So. So, so someone said A. So A is close. So we need to take the delta H formation of this times 2 minus the delta H formation of all of this stuff. However, these are all elements. We have sulfur in the elemental form. We have oxygen in elemental form. This is all just 0. So all this is the enthalpy of formation of SO3 times 2, because we have a 2 coefficient, right? So we go over here, negative 395.2 times 2, so is negative 790.4, so it's E. Okay? Let's take a break now. So how about we just take a break until 8 o'clock? So let's come back at 8 o'clock, okay? So everyone's here now. So, okay. So now we're going to talk about the second law of thermodynamics. So this part might be a little bit difficult, but don't worry about the mathematics too much. Just try to have some qualitative understanding of what's going on, I guess would be a good advice. Okay, so what's the second law of thermodynamics? The entropy of an isolated system will always increase because of statistics. Entropy, you can think of it as a measure of disorder. Strictly speaking, it's a measurement of how many microstates a system can have. So like how many different possible states the system can exist in, microstates. So entropy, but for now you can just think of it as a disorder. So the disorder of an isolated system will always increase. Well, what is an isolated system? An isolated system cannot exchange heat, work, or matter with its surroundings. Well, the universe doesn't have surroundings. Everything is in the universe. So for at least in our understanding of the universe is a closed system, an isolated system, I should say. So that means the entropy of the universe will always increase. So, for example, here we have two pictures. One, we have a container of gas, where all the gas is in one corner, and one where all the gas is distributed freely and randomly. So which one of these happened first? Well, this one has more disorder, more entropy, so it will move in the direction of more entropy. So we can say this is like the arrow of time. We can tell which way it is, what way time is going. Another example, if you tossed bricks off a truck, you're going to get disorder, right? It's very unlikely that if you just throw bricks on the ground, they will stack up neatly. So, for example, do you think the melting of water, okay. So entropy is usually represented by the letter S, right? For some weird reason. And of course, just like delta H, we have changes in entropy, okay? So just like with delta H, we can add, subtract delta S. But the main difference between here is because the value of enthalpy, the value of internal energy, the value of enthalpy or internal energy cannot be determined. We cannot determine the exact value of enthalpy. However, we can determine the exact value of entropy. So we have S naught. So S naught is the entropy per mole of substance out of, course, standard conditions. Yeah. So this is because because strictly speaking, you can say entropy is actually equal to the Boltzmann constant times the natural logarithm of all of the microstates of that system. So because the number of microstates is some number, it actually turns out that we can determine entropy exactly. And you have to do some pretty complex thermodynamics to find this value, but we can find these values and we can tabulate them. And this allows us to calculate the delta S of reaction for any reaction we want. So we have, yeah. So delta S of reactants. So delta S products minus the sum of the entropies of the reactants. And this will give us the standard entropy of reaction. So this is the same as delta H. So this formula is very similar to the formula we saw for delta H, but instead of enthalpies of formation, we use standard entropies. Got it? Okay. So let's put all of this stuff together. And of course, this is for a constant pressure process. Let's say we're a chemist and we want to figure out, will a reaction go forward or not? Is the reaction favorable? Well, we know that the entropy of the universe will always increase. That means that the sum of the delta S of the system and the sum of the delta S surroundings must be greater than 0, because the system and surroundings comprise the entire universe. The S of the system is just the entropy of the reaction, which we can find using a table of values. But how do we calculate delta S of the surroundings? Well, we have that, so Q of the surroundings equals negative delta H of the system by the conservation of energy. So, and it turns out that the delta S of the surroundings equals Q over T. And the surroundings are huge, right? The surroundings are like the entire universe. So the temperature of the universe will not change depending on whether the reaction will not change the temperature of the universe. So we can treat temperature as a constant. So this gives us delta S system plus negative delta H system over T is greater than 0 for a favorable reaction, for a spontaneous process. And then we usually multiply this expression all by negative T, and we get this. Delta H minus T times delta S must be less than 0 for a spontaneous process. And we call this Gibbs free energy. So write this down. Gibbs free energy. Okay. One minor note about spontaneity. So spontaneity basically is like, given an infinite amount of time, will the reaction go forward? And if the reaction is spontaneous, yes. But however, spontaneous reactions are not necessarily fast. So for example, the conversion of diamond to graphite is a spontaneous process. But that reaction doesn't happen in real life because it's just too slow to observe. No one has ever seen a diamond turn into graphite. Okay? So spontaneity really has nothing to do with kinetics. Okay? So let's consider the signs of delta H. So delta H can either be positive or negative. Likewise, delta S can either be positive or negative. So then, depending on that, we get the sign of this term. And then we can find the sum of the sign of delta G. And if delta G is negative, the process is spontaneous. If delta G is positive, then the process is non-spontaneous. And you might notice that if we have a negative delta H and a positive delta S, then we have a reaction that will always be spontaneous. So favorable reactions will usually have a negative value of delta H and a positive value of delta S. For example, the combustion of gasoline with oxygen is a highly spontaneous process because we're creating a lot of gas molecules. We're turning gasoline, a liquid, into water vapor and carbon dioxide. So we have this large increase in entropy. Additionally, the combustion of gasoline releases a huge amount of heat. So so delta H is also going to be negative. But here we have non-spontaneous processes. Non-spontaneous processes, so we have positive delta H and a negative delta S. These will always be non-spontaneous. For example, the formation of ozone from oxygen. So O2, so 3 molecules of oxygen go to 2 molecules of ozone. So we're decreasing the amount of gas particles. We're decreasing the disorder. So delta S is negative. And it's actually energetically unfavorable, so delta H is positive. So ozone is very highly unstable, and it's very unfavorable to form ozone. And of course, we have these cases where we have these reaction characteristics. So I'll give you just a minute to copy down this table. So just copy down this table. Characteristics. Okay. So how do we relate this to equilibria? So delta G equals the delta G naught. So delta G naught means at standard state. So all concentrations are equal to 1. All pressures are equal to 1. And temperature is 298 Kelvin. Plus RT times logarithm of the reaction quotient. Okay. So, and we can turn this. So let's say, so once the reaction has reached equilibrium, nothing happens, right? Because everything's in equilibrium, nothing happens. In other words, delta G is 0. Once delta G reaches 0, nothing happens, right? Because there's no change in free energy. So I should probably clarify what Gibbs free energy means. So Gibbs free energy is the amount of work that the system can do. So once delta G equals 0, nothing happens. So, and at equilibrium, Q equals KEQ, right? So we have so I want you to remember this. Delta G naught equals negative RT ln K. Law is the natural logarithm, of course. Okay. Okay. And I thought there's one more slide, right? It seems like it didn't get uploaded or something. Well, there is just one last thing I want to talk about before we go into problems. So Le Chatelier's principle. We have, let me just do a derivation. So we have negative RT ln K equals delta G naught. Therefore, K equals E raised to the power of negative delta G over RT. And delta G equals delta H minus T delta S, right? So we plug that into here. And then, of course, we can split this. So we have this equation, which I've derived. And of course, this is a constant. So this is just some constant, which I'll just write as C. So what's the takeaway? Okay, so we have this, KEQ equals this times some constant. And this means that depending on the sign of delta H, depending on whether delta H is positive or negative, the reaction will respond in different ways to temperature. So let's assume that delta H is some positive value, is some positive number, so N, right? So then we have KEQ equals e to the KEQ equals e to the negative N over RT. Okay. So what happens as we start to increase the temperature? When we increase the temperature, this whole term becomes less negative. Therefore, E will increase. So if delta H is positive, if delta H is positive, when we increase the temperature, we increase the equilibrium constant. And the opposite is true if delta H is negative. Why is this? Okay, well, you can think of it as this way. So some reaction, let's consider delta H is positive. Then we are inputting heat into the reaction because we're increasing the enthalpy, we're increasing the internal energy, so we have to put in heat. So heat plus reactants goes to products. Therefore, when we increase the temperature, we're increasing the reactants, which shifts the reaction that way, which forces the reaction that way. If delta H is negative, then we release heat because we're lowering the enthalpy, we're lowering the internal energy. So this energy has to go somewhere, so it gets released as heat. So when we increase the temperature by increasing heat, we force the reaction in that direction. Does that make sense? Okay. So basically, and this is Le Chatelier's principle. Le Chatelier's principle. And so, yeah. So just to give you a qualitative understanding of how the equilibrium constant will respond to changes in the temperature. So I think now is a good time to we can start doing some problems. So these are just simple multiple choice questions. So 1, what thermodynamic quantity expresses disorder in the system? Okay. So can someone tell me, so what expresses disorder in the system? So look back at your notes. Entropy, right. So entropy expresses disorder. Internal energy is self-explanatory, and heat flow really doesn't have, that's not really directly related to disorder. Same with enthalpy and bond energy. Okay. So, which one of the following is always positive when we have a spontaneous process? Lighting should be really bad. So remember, the entropy of the universe will always increase, right? So the entropy of the universe will always increase. So this will always be positive, right? Okay. So which of the following has a positive delta S? Which one of these reactions increases this order? So let's consider this one by one. So here we have 3 gas molecules turning into 2 gas molecules. So we're combining things together. We're turning 3 into 2. Do you think that will increase or decrease this order? Great. We have a decrease in this order. So because it's a decrease in this order, it's not that. What about this one? We're turning 2 things into 1. Right. So we have another decrease. What about this one? We're turning from a rigid solid into these ions that move freely in solution. So we have an increase. Great. And this corresponds to a positive delta S. Okay, which of the following, so I'll let you guys look at this one. Which of these decreases entropy of the system? Okay. Yeah, C, because we're turning this free-flowing liquid into this rigid solid. We're turning into a rigid solid ice where all of the water molecules are held in place in a solid. This one's a bit tricky. So which one of these has the largest standard entropy? So it turns out that heavier molecules and more complex molecules have more disorder because there's more things to wiggle around. And this is somewhat complicated because it turns out that when the molecule gets larger, its mass increases. And it turns out that the spacing between energy levels also decreases. So more particles can occupy higher energy levels, and which increases disorder. So clearly the most complex molecule here is C. So it turns out C is the correct answer. Okay. So can we do this problem? 6. Can you just do 6? So delta S okay, so you get the formula here. Okay, so E, right, great. And we actually don't even have to do any calculation to get this result because we notice we have 2 molecules of gas going to 1 molecule of gas. So we should expect a large decrease in entropy. So hence negative 112. But we can do the calculation out. So this calculator doesn't have a super good screen. So let me use a different one. Right. So we go to calculate. So we need to take the entropy of the products. So C2H4. So C2H4 is right here. 19.4 minus, and then we need to find the sum of the entropies of the products. So 130.58 plus 200.8 equals negative 112. Okay. What about 7? Can we do 7? Okay. So a great way to visualize this is actually like this. So here we have free energy, so it gives free energy. And on the one side, we have pure reactants, and here we have pure products. And as we go from, the free energy will decrease as the reaction progresses, but then it will actually increase some amount. And obviously in between here, we have a mixture of reactants and products. This mixture corresponds to some equilibrium. And the system will want to reach a minimum of free energy. And it will achieve that at some mixture of products. And this is the equilibrium. Once we've reached this point, we've reached equilibrium. And notice that we have not gone completely from reactants to products. So the reaction is not necessarily complete. The system entropy is not going to be 0. We can't have zero entropy. It really only happens at 0 Kelvin. I don't know what that means. And the reaction and thermodynamics has nothing to do with kinetics. So C is the correct answer. So we already did this one. Okay, 9 is a bit more complicated. So let's break it down into steps. First, calculate delta H, and then calculate delta S. And then remember delta G naught equals remember that. So can we do problem 9? Just give me a second. Yep, can we do problem 9? Wait, so this is one way to do it. I just realized that they actually give you the delta. They actually give you the delta G as a formation. So you can use this. Right, you can use this data. And the delta G of formation of any pure element is just 0, since you don't get any free energy by doing nothing. So this is all just 0. So all we need to do is consider this. So we go under POCl3, find delta G of formation, negative 502.5. However, we have a coefficient of 2 here, so we need to multiply it by 2. So the answer should be negative 1109. Okay. So simpler than, okay. So what about this one? I just showed you a similar diagram. So number 10. Oh, sorry. Because at C, we've reached the lowest free energy, right? This is the lowest energy state. It's favorable. Okay. What about 11? Can we do 11? Delta G equals. Right. Oh, I'm gonna get a glass of water. Can you hold on a sec? We want a spontaneous reaction, so delta G should be negative. So let's imagine that T is some very small number. Then we could ignore this term. And then we have delta H, and then delta H is positive, so delta G will be positive. So it will be unspontaneous at low temperature. At high temperature, this term starts to be important, and this term will be negative, so it will be spontaneous at high temperatures. Great. What about 12? Can we do 12? So it's non-spontaneous at low temperature, so we have a positive delta H, but it's spontaneous at high temperature, so we need a positive delta S, so that this term can become very large negative number. So great, A. And 13? I don't know, maybe someone else should do, can try to put 13? Someone else can try to do 13? Spontaneous at all temperatures, right? Yeah, great. So that means delta G should always be negative. And if you want delta G to always be negative, these two terms, this one always needs to be negative, this one always needs to be negative too. So this would imply a positive delta S, and a negative delta H. Can we do 14? So you need to calculate delta H and delta S. And then from that, you can make judgments on the spontaneity. So 14 actually doesn't require any calculation, really. You can do it entirely without calculation. So just based on your intuition, so we're turning titanium tetrachloride. This in the industry, titanium tetrachloride actually has a nickname, tickle. So we're turning tickle from a liquid into a gas. So we're turning something from this a liquid where all the molecules are close together into a gas where all the molecules fly around very quickly and very randomly. So what does this say about delta S? Are we increasing or decreasing this order? All right, we're increasing this order. So delta S should be positive. What about delta H? We need to put in energy to break the bonds between, to break the forces of attraction between the liquid molecules. So, is it positive or negative? Is delta H, is enthalpy increasing or decreasing? So it takes energy to break the forces of attractions between molecules. So enthalpy is increasing, so delta H is positive. Okay, so based on these two values, what's the correct answer? What should we conclude based on this? Non-spontaneous at low temperature and spontaneous at high temperature. Great. And this actually makes intuitive sense, right? Because at low temperatures, stuff doesn't boil, but at high temperatures, stuff starts to boil, and you start to turn liquids into gases. Great. Okay, last page. So can we do this one? So I'll give you like maybe 5 minutes to try to think and do the problem. Think about the problem and do it. We want the temperature when the reaction becomes non-spontaneous. In other words, we want the transition point when delta G goes from negative to positive. Let me see if I can graph this. So imagine we have a graph like this. Okay. And so we have so the delta G equals delta H minus T delta S. So this slope equals negative delta S. And the x-intercept, the y-intercept is delta H. So we want the point where this equals 0. We want this temperature. So this is very easy to do. All we need to do is set delta G equals 0. Now solve for delta H, delta S, and calculate temperature. So let's do that. So, how do I make it brighter? We need to solve this equation. So let's first find delta H. Does anyone know what delta H is? So it should be the enthalpy of formation of this minus the enthalpy of formation of this minus the enthalpy of formation for that. So this is easy enough to do. So negative 127 minus negative 167 minus 105.9. So negative 65.9 kilojoules. This is negative 69.5 kilojoules. You have to watch your units because entropy is in joules, delta H is in kilojoules. Let's do the same here. 96.11 minus 56.5 minus 73. It's better if I express it this way. It should be minus 56.5 plus 73.93. But of course, the minus sign distributes across the parentheses. So it's the same thing. So that equals negative 34.32 joules. So now we can solve this, and I don't feel like actually solving this. So I'll just use the solve function. So 0 equals negative 65.9 times 1,000, because there are 1,000 joules in a kilojoule, minus temperature times negative 34.32. Solve for temperature, solve for T. And then, so we get 1,920 kelvins, and we need to convert this to Celsius. And when we convert to Celsius, we get D, right? Because 1,920 minus 73 is, 1,647, close enough. Okay. So, now 16. 16 is somewhat of a trick question. I don't think they want you to calculate the equilibrium constant. However, the equilibrium constant is dependent on temperature, which is not given, so you need more data. Okay? And can we do 17? Delta G equals negative RT1K, right? So we just rearrange this to get K equals E to the negative delta G over RT. Now, can someone solve this? Can someone evaluate this? What's K? Oh, never mind. They want delta G. So just plug it into here. So what's delta G? Into the calculator. So negative 8.314, which is R, times 298 Kelvin, times the natural log of 5 times 10 to the 8 equals negative 25 kilojoules. Oh, wait. Oh, I put a plus sign here. That should be times. Negative 50. Yeah, negative 50 should be A. And finally, let's just do 18. So we need to find the value of Q. And Q for here equals the pressure of NH3. And what should the power here be? raised to what power? Does anyone remember? 2. Great. Divided by and that equals 0.65 squared divided by 1.6 cubed divided by 1.9 atmospheres. And then all we have to do is say that delta G equals delta G naught plus RT ln Q. And then that, of course, equals negative 33,000 plus 8.314 times 298 times the natural log of 0.0543, which equals negative 40, which equals C. And that's it. So I think that's the end of the lecture. So if you don't have any questions, we're just going to end here.